Okay, I see that still a few people are joining in, but I think this is the time where we should start. So let me just introduce the speaker. Today's speaker is Chiara Marletto, who is a research fellow at Wolfson College and at the Clarendon Laboratory, University of Oxford. She's working on a number of fundamental problems in quantum theory, information theory, thermodynamics, and these include the constructor theory, which is a proposal to generalize quantum theory of computation. So today, Chiara is going to tell us about very exciting work that she had out this summer, which has to do with this kind of mythical phase, the Aharonov-Bohm phase. So, okay, with that, Chiara, I'm going to hand over the virtual floor to you. Thank you very much for agreeing to give this talk.
Thank you, David, for organizing this and for the invitation, and for thank everyone for joining. So I think I like this this expression you use to say that this is a mythical phase, because yes, it is a mythical phase, and I think it's one of those things that you probably come back to when you are first you learn it in textbooks, and then you sort of revisit it later as you understand maybe quantum theory better and better, or maybe not. But let's say it's a really it's like a milestone that was kind of placed at some point in the progression of physics, and it's very nice that you can somehow revisit it and maybe find something new or surprising to say, or different, let's say. So the reason why I kind of was interested in this topic is because part of my work is very much centered around the idea of formulating physics through physical principles rather than through dynamics and so on. And so the principle of locality kind of features quite a lot in my work. And so I want just to start with this, that in quantum theory, and this is largely true in relativity as well, locality in this form is satisfied in this form of no action at a distance. So you can always say that if you have two subsystems A and B, and you have like a unitary or in fact a more general transformation, this holds for a CP map as well, that operates on only one of the two subsystems, let's say A, but not the other one. This transformation can only change A's quantum numbers, quantum observables, and not B's. And I think you can see this very nicely in the Heisenberg picture of quantum theory and quantum field theory. And then you can prove out of this the theorem of no signaling, and the fact that even in fact in non-relativistic quantum mechanics you have this nice property of no signaling, which is kind of saying that even non-relativistic quantum theory somewhat sniffs relativity. And of course, when you say this, well, one thing that comes to mind is Bell non-locality, but we know that kind of non-locality is maybe a misnomer in a sense that it really just refers to the fact that we cannot describe quantum theory with local hidden variables, real valued hidden variable models. And then the other thing that comes to mind is the Aharonov-Bohm effect, which is about a different type of non-locality. And this, I think, was already was presented, let's say, in this way since the start, since when it was discovered. And that's the kind of thing I would like to challenge a little bit in this talk. And in order to challenge it, I have to introduce a different notion of locality, which is also relevant to the discussion. And in fact, I would say it's a consequence of this more deeper principle of locality that I just wrote down here. And it's the question, in fact, it's the fact or the question, because the Aharonov-Bohm effect seems to put this fact in doubt, is the fact that all phases are locally acquired. Well, what do I mean by that? I mean that, so if you think of a simple interferometer, like a Mach-Zehnder interferometer with some sort of charge or let's say a photon, depending on what kind of system you're considering, let's say a charge which goes through it. And then if you draw an imaginary line at each point along the path, like this one, if there is, let's say, a background field with, different values at different points, you'll be able in general to notice that with respect to the situation where there is no field, the charge will pick up a phase difference along the two paths. And this phase difference is nicely measurable by doing a number of things. So you can close the interferometer and check the interference fringes at this port, which will be different and it will depend on the value of the field along the path. Or you can also imagine a sort of a very complicated experiment, but let's say an in principle possible experiment where you stop the charge halfway through and you have lots of these interferometers, an ensemble of them, and then you can reconstruct tomographically the charge at this point. And this is, of course, in principle allowed by the fact that you can measure local observables of this charge if you think about it in the, say, second quantized picture. Anyway, so the point is that there is a picture that says that phases are acquired locally point by point. So at every point where the charge is the phase, there is a non-zero value of the field that accounts for the presence of this phase difference. So the Aharonov-Bohm effect seems to be the only problem, in the sense that it seems to be the only phase that doesn't follow this pattern, this kind of explanation. So the traditional account of the AB effect is that there is an apparent paradox with this phase. So just to summarize, to kind of recall what it is. So you have an interferometer. This very sketchy drawing is just like an interferometer, what I drew in the previous page in more detail. So you've got a charge particle, which kind of is put into a superposition around a perfect solenoid. So it's kind of an infinitely long solenoid at this point. And you then measure the interference fringes when you close the interferometer for the charge. And this very surprising thing is that although where the charge wave function is non-zero, there is no field, particularly there is no magnetic field. The charge interference pattern is affected by features of the solenoid, and specifically it acquires a phase which can be written in one of two ways. So it can be written as being proportional, let's say, to the flux of the magnetic field through the cross section of the solenoid, or it can be written as a line integral of the vector potential along the path on a closed loop like this. Now, this is problematic or puzzling for a number of reasons. The first reason is that the fact that, so if you want to go by the normal account and say that the phase is locally acquired, you find a little bit of a difficulty in the sense that there is no field where the charge is. So how can it pick up remotely, as it were, this phase? So it kind of can feel the presence, let's say, of the B field, even though the B field isn't here, but it's there at the solenoid point. And the other problem is that if you really insist on having a local account, in the sense that you want to explain the phases being caused by the interaction of the charge with some local feature, something that is present as along its path, then you can resort to the vector potential. But the vector potential is, as we know, it's it's a gauge-dependent quantity in general. And so it seems like you have to resort to things that are not as real as fields, at least in classical electromagnetism, in order to account the phase for the phase in a local way. And I think lots of things have been written about this topic. And before entering the final little addition that my work with my collaborator Vlatko Vedrov makes to all of this kind of interesting story, I have to tell you another bit of the story, which is a more recent one, and has to do with the fact that there was a very interesting model that was proposed in order to explain the AB effect only in terms of field-field interactions, so without resorting to the vector potential, and in a way that appears to be involving really an interaction between the field of the electron and the field of the solenoid. And how can that be? Well, so Lev Vaidman had this very beautiful idea, I think, to consider what I think it's nice to call the back action of the electron, which is superposed across two locations on the solenoid. So in his explanation, the electron, it's true that it doesn't have any, any field of the solenoid being non-zero at its location, but the electron has produces some electromagnetic field around itself. And in particular, there is part of this field which interacts at the point of the solenoid with the solenoid itself. So you have the field of the charge BC and the field of solenoid BS at the point of the solenoid, which are non-zero. And you can notice that when the electron goes on this arm, as it were, in this branch of the wave function, it's having one effect on the solenoid. And when it's on the other branch, it's having the opposite effect. So for those who kind of like this picture of quantum information or entanglement, what's going on here is that there is a controlled gate between the charge and the solenoid, whereby the charge does something to the solenoid if it's on the right path, and it does something else on the solenoid when it's on the left path. As a result of that, you create an entanglement between the two, vanishingly small entanglement, of course, but there is some. And this is what Vaidman uses to explain the phase. And you can rewrite the phase that's acquired, let's say the phase difference between the phase of the wave function of the electron at this point and the phase of the wave function of the electron at this other point in this way. And what I want to kind of stress here is that this epsilon is nothing but the total energy of the total electromagnetic energy of this system, where you consider both the charge and the solenoid together. So it's all explained in terms of now B and EE type of contributions. So it's a different explanation from the first one that I gave you. And it's interesting because it suggests that there is some kind of back action of the electron on the solenoid. Now, Vaidman was very happy about this, and I think on the back of this work, more work were proposed by Kang and collaborators, noticing the fact that this treatment is more explicit, that there is a gauge-independent measurable phase difference at each point along the path of the electron, which wasn't so obvious in the other treatment, whereas it is in this one. Because this value, of course, is value of energy, of the total energy, is well defined along the path for each point along the path. So it seems like we are more or less recovering the same local picture that we have for all other phases. But is that true? And here is where I think the story about our work starts. So I think there is still a residual non-locality in the work that Vaidman proposed, in that, yes, it's true that the phase is created by the interaction of the electron field with the solenoid field at the point of the solenoid. But then, of course, the phase is now recoverable point by point along the path of the electron. So how is it supposed to travel or to move from the solenoid back to the electron? in a way, you have a mechanism that says the phase is created over here, but then you can detect it along the path. In fact, so you can detect it on the charge when it's closing the loop. And so that's the kind of question that I would like to focus on. So can we remove this residual non-localities? Is there a way of doing that? And the answer is yes. And it's very surprising or fun, I would say, that the solution to this problem comes via kind of using a fully quantum model that treats that adds, let's say, a third quantum system to the picture. It's not just the fact that the electron is quantum because it's superposed, and the solenoid is somewhat quantum because it has to respond to the back action of the field of the electron on the solenoid itself. But of course, there are the photons. The electromagnetic field is mediating this interaction. And although in the classical picture it's treated as a classical static background, it can be quantized. And so you can have a third quantum system, which are the photons, which basically mediate this phase. And once you quantize the electromagnetic field, you have a nice picture, which I try to represent here kind of in a diagrammatic way, where, so this is, let's say, the path of the charge on one of the two kind of sides of the solenoid. Here's the solenoid. And then there's F, which is basically a third subsystem that acts as a vector. So the photon field is the thing that causes the phase to kind of go back, as it were, to the electron and then make it available on the charge for later detection. And so you can actually think of a gate or like a unitary transformation in some kind of approximation, if you like, where there is a kind of two-body interaction between the charge and the field, and there is another two-body interaction between the field and the solenoid. And if you consider the combined action of these two-body interactions, you get this nice interaction that overall makes the phase, the AB phase, be available on the charge. And here is the Hamiltonian that you can write down, which is nothing but something like P dot A and J dot A. So it's here you see the free energy Hamiltonians, the charge, the solenoid, and the field. I'll go back in a moment to these Qs to explain what they are. And here you have a term which is, if you look at it carefully, you will see that this is P dot A. So the integral and this part is actually the A potential. Quantized, so it represents the photon field. And here you have J dot A as well, and J is some kind of current density for the solenoid. So here you have the charge field interaction, and here you have the solenoid field interaction. And these Qs are just are qubit operators that I inserted in the model, because to write a fully second quantized Hamiltonian, I should have put some number operators for the charge and the solenoid as well. But because we are in a kind of low energy regime, we don't really need to think of creation and annihilation of particles. And this is simply a kind of simplified algebraic model to treat the charge and the solenoid, and indicate that in principle the charge can be superposed, and in principle the solenoid can be superposed itself. So these are just kind of Pauli operators for the charge, the solenoid, and they are kind of simplified version of what the full Hamiltonian would look like, where you would have number operators here. So this means basically if there is a charge, so if number operator for the charge is 1, let's say, then this interaction happens where the charge kicks the field in some way. And likewise, in this case, if the solenoid is present, then this other interaction occurs between the solenoid and the field. And as you see, this is nicely local, and it has the photons as being the mediators of the interaction. And you can compute you can diagonalize this in a kind of exact way, and then you can do some kind of calculations for what happens if you have your starting point as the vacuum, and then you will see for the field, and you will see that the phase on the charge appears in the way that you expect. So what this shows is that, so if you, just to clarify, if you then do this for each point of this path, so for, you cut at this stage and you check what's the phase difference between the, let's say, the wave function of the electron on the left side and the wave function of the electron on the right hand side, which is what I wrote here. So 0, let's say, represents this part, and 1 represents this other side. This Hamiltonian, when you compute its action and then you just consider the charge part of the system, will give you a phase which is such that if you integrate on the full loop, will coincide with the full AB phase. The difference in the explanation is that this phase is locally generated by the photon mediating the interaction between the solenoid and the charge. And the fact that you now quantize the field allows you for a very interesting final punchline to be reached, which is that you now have a very direct way of checking whether the phase is really present along the path and is gradually acquired or not, which is, I think, the second point of this work that I wrote. So to see that, we need to do a little bit of thinking. So I'll try to do it in some, with some logical steps, and then we can talk about the details maybe in the questions. So first of all, let me rewrite this state, which is in first, here I wrote it in this first quantized picture, which is maybe not so illuminating. But you can, with this arrow, just means switch to the second quantized picture. And in the second quantized picture, you can write a superposition of an electron, or in fact of any particle, across 2 points, left and right, as an entangled states of modes. So this 0 is just the vacuum on the left mode, and this 1 is a creation operator that acts on the vacuum, indicating that there is a particle on the right. So this is like one branch of the wave function corresponding to the case where the particle is on the right, because it says there's 0 particles on the left and 1 on the right. Plus phase, the other term where the particle is on the left and there are no particles on the right. So you can just rewrite the same state in this other way. And this suggests something interesting, that you could try to perform some sort of tomography on these modes to extract this phase, the same way that you do, you could in principle do that with say, a photon, for example. Unfortunately, this idea doesn't quite work directly in that way. So the idea would be something like, let's stop the interferometer at this point, and somehow let us use some local means to measure local observables of this mode only and of that mode only. And then let's build statistics up in order to reconstruct this phase. This is done, it can be done with photons, with local oscillators and so on. With electrons and charges in general, but let's stick to electrons because that's maybe the most direct way of dealing with this thing. With electrons, there's a problem because being them fermions, they are subject to these super selection rules, which unfortunately do not allow for the observables that you would need in order to extract the phase locally to be measured directly on one electron, because these observables are not really, these operators are not really observables, and you cannot quite implement a measurement of them directly on a single fermion. So these superselection rules have to be somehow circumvented. how do we do that? Well, one way of doing it is to think of using a second electron as a reference. So this is a second electron which we are using as a reference. So we are preparing a state. Of course, this experiment is extremely challenging, and I'm not suggesting this is something that can be done easily, but let's say in principle, it appears to be possible. So you have like the solenoid is off and you create this superposition, and then somehow you stop the electron at that point. Then you switch on the solenoid and you bring it to the desired B field value that will then generate the AB phase. And of course, this second electron will pick up some phase, but this phase is controllable in the sense that you can compute what it is, and it's not an AB-like phase because it's due to some non-zero value of the field due to the transient. And you can just kind of compute that and know what to expect. And then you can prepare a second electron, which is now the electron that I was talking about here, the one that will pick up this delta phi r, which we want to measure. And then consider the joint state of the two electrons at this point, which in the second quantized picture will be described by a state of this form. So you've got the electron, which is the one that picks up the phase, the electron A, and then the reference, which is here, with some fixed phase, which I didn't write here because it's a kind of an offset that can be controlled, and therefore I can put it to 0. Now, if you rewrite this in a nice way, you can see that the phase, the relative phase, appears in each in a subspace where the superselection rule is satisfied. So in this subspace, you have two fermions, and in this other subspace, you also have two fermions. And you can measure observables pertaining to both electrons on the mode L and on the mode R, therefore locally to L and R. And this allows you to extract the phase in this local way through some sort of tomography. Of course, I'm not talking about single shot experiments. This is, you need an ensemble of these objects to be able to extract the phase. So to cut a long story short, I think this allows you to extract this value of the phase point by point locally, which is what we found very exciting. So to conclude the kind of presentation of this work, there are some kind of points that I think are important to take home in a way. So the first point is that this issue of whether you could find a field-only expression for say, a Hamiltonian that describes an interaction between charges and electromagnetic fields, which is what, let's say, Vaidman was concerned about, because that's what his model was motivated by. I want a model for the AB effect that only uses fields and not potentials. Is actually a different issue from the issue of is the AB phase acquired locally, which is somehow, I think in some part of the literature, so these two issues were confused, or at least not clearly separated. So Vaidman's model kind of addresses the first issue, whereas in this work, we are trying to use his model, quantize it, and show that the second issue is also not an issue, the issue of locality. So this model that we provided is actually quantum, and because it's quantum, allows you to account for this local generation of the phase, and also allows you to see a direct way of extracting the local value of the phase point by point along the charge path, as much as you would do with any other phase. And then there are two pieces of work which are interesting. So there is a work by Pablo Saldaña who kind of suggested yet another way of extracting this phase by this local phase point by point, which is very interesting. So I'm just kind of flagging it up. And then there is a further point of work that Saldaña and myself and Vedral also kind of addressed recently. That, I mean, you could wonder what happens if you have like variants of this AB effect. What happens with the Aharonov-Bohm effect, or what happens with, say, this situation where you have a superconducting ring around the solenoid, which appears to completely shield the fields from the charge. Well, you can apply the same quantized description, and you will see that because you're treating the field as made of Q numbers now and not of C numbers, the interaction with the shield is such that the shield doesn't really fully shield, in the sense that although the field inside the superconducting shield is zero, just like in this case, the Q number interaction between the photon field and the field of the quantum observables of the solenoid, the quantum observables of the shield and the quantum observables of the charge are always on, because these are quantum numbers, so they can't be all zero at the same time. And this is what allows the phase to filter through, even though there is no net force, or there is no kind of way of classically account for this fact. So the third point that I'm trying to kind of get across here is that the quantum model is really needed to see what's going on. And if you try to use the semi-classical model, you will, one way or another, miss some parts of this kind of account that has locality in it. So to, sorry. So to kind of conclude, this is kind of my punchline. In my view, I think there is no really residual non-locality in physics, provided, of course, that one makes sure that you know, you quantize all the systems in your kind of overall system. If you don't, you will see some inconsistency of sorts, and sometimes this inconsistency pops up as non-locality. And then this suggests that somehow locality is a good universal guiding principle, which is provided by all quantum phases. And so you can also think of it as a nice base to construct maybe future theories of physics that go even beyond quantum theory. And with that, I think I'll just stop here, and thank you for listening. I'm very happy to take questions.
Okay, Chiara, thanks a lot for this super interesting talk. I can see that we have a question from Ulrich Snyder. So let me just promote you to panelist, and then you should be able to ask your question live now.
Hi, Chiara. Many thanks for this very interesting talk.
Thank you.
I have a question about like another type of non-local phases, and these are phases that are like local in momentum space. So when you think of, say, topological insulators, you have these Berry phases if you like go once around the pre-Lorentz zone. So basically, fundamentally, it's a question about like Berry curvature. Berry curvature is something that's local in momentum space and gives rise to a phase, but because it's local in momentum space, it seems to be non-local in real space. Did you think about this as well?
Yes, so I think when you talk about locality, no, I haven't thought specifically about this, but I think so first it would be interesting to extend this treatment to these phases too. The only problem is that, so when you talk about locality, there is a sense of locality which holds in any basis, in the sense that if you take, say, the momentum basis, and you have a Hamiltonian which only couples let's say, two modes in momentum, you don't expect others to be affected by that Hamiltonian. So that locality is still valid in that case. Yeah. Of course, there is the fact that we have a predilection for position basis as being the one where we talk about locality, because it so happens that position is the basis is picked out by the I would say by the Lagrangian, or the kind of global interactions that we have at the level of the universe, right? Yeah, exactly. So in that sense, I think you could still prove locality for sure in the momentum basis, but I don't know what it would look like in the position basis. So I think this is kind of an open question, and I don't know the answer, but it's an interesting one. I think the Berry phase has lots of similarities with the AB phase to some degree. But somehow, unlike the AB, I think it was only the AB phase that was somehow used as well, as a kind of was by some people, I think some physicists regard it as an example of a different kind of non-locality compared to the Bell type non-locality. And the reason why we focused on that one was because there is this weird element of the fact that classically the field on the electron or the charge is zero. There's no such field, and then you kind of have to explain why is it that you get what you do get. So it's a good question. I don't know the answer of directly, but I think it would be nice to extend what we do to that. Thanks.
Thank you very much.
Thank you.
Okay, we have another question from Alexander Lasek, but just before that, I should mention for everyone who joined the presentation a bit late, if you want to ask a question, just pop your name into the Q&A, what to call it, the button, press the button and then ask your question there, and I'll promote you to a panelist, so you can ask your question live. Okay, Alex, you should be, you're on the panel.
Yeah,
okay.
I'm on. Hi, Chiara, thanks for the talk.
Hi.
I wanted to ask, have you considered how relativistic effects can play into this? So if the path was space like separated from the solenoid, or if the speed of the charge was relativistic, or if you maybe switch the solenoid on halfway through, how would that affect the phase shift?
Yeah, that's a nice question. I think the treatment is what we use is in a way standard quantum field theory with an approximation which is an adiabatic approximation. So somehow the way I presented this was we made this approximation that the charge is going very slow, and we can somehow take a cut and then represent the interaction at that point with the Hamiltonian that I wrote down. Now, I think modulo this approximation, which I think is kind of standard in AB, the full treatment should be relativistically compliant. So in a sense, whatever we get in this particular way of representing it should be true of other kind of settings that you can think of. It goes through with the Aharonov-Bohm effect. And in regard to the other question that you asked, which is a more maybe kind of a variant of the experiment, what happens if I switch off the solenoid halfway through? Then that's actually an interesting question. And I think the model we have presumably produces one answer, and the traditional model produces a different answer. In fact, you could ask the same question. The question of what happens when you switch off the solenoid halfway through is a good question for noticing that the traditional model is a little bit insufficient, in the sense that when you try to model that in the way when you have a classical background, you will see that you will encounter some issues in describing the dynamical transient of what's going on. Whereas in our case, because we're treating everything with photons and so on, yes, it might be complicated, but I think it will just go through in the standard way of quantum electrodynamics. And although I haven't done the calculation, I think this other paper that I mentioned, the Saldana paper, does, so the first one where Pablo is kind of considering another way of testing the presence of this phase halfway through, precisely considers the case where you are switching off the solenoid at some point. So if you want to see the details, I think you can find some of them there. There are other experiments you can think of which are also interesting. So you can think of slowing photons down. So we were thinking at some point of putting like a different medium between the solenoid and the charge, whereby the photons are not propagating as fast as you expect in vacuum. And then this also should give some kind of different answers to the kind of classical treatment. So all of these things are possible, and I'm sure there are more surely smarter arrangements of the experiment than the one that I just discussed. In a way, that's maybe for future research. That's a nice question. Thanks.
Thank you.
Okay, let's see. Do we have any other questions from members of the audience? I think I have a question that I could ask meanwhile then. So you mentioned that this is a different type of non-locality that has been discussed compared to Bell non-locality. And a couple of years ago, I did some work on something called interaction-free measurements. I don't know if you're familiar with this.
Yes.
Which costed, like, so essentially, just for people in the audience that maybe don't know what this is, but you can imagine it as a Mach-Zehnder interferometer, but you stack more and more beam splitters on top of each other, and then if you place an object in one of the ends of this extended Mach-Zehnder interferometer, your probing particle will end up at the lower input of your Mach-Zehnder interferometer, and if you don't place a particle, it will end up in the upper end. And this happens without the particle actually ever significantly interacting with the object that's placed in the Mach-Zehnder interferometer. So in a way, you can, doing some clever rearrangements of this, you can like place, you can like define your spatial Hilbert space in such a way that it has 3 components, and your probe particle will never interact with this object that you put in, which is put in one of these 3 spatial Hilbert space components, and still something happens to the probe particle that sits in the other 2. Is this something that, like, would this go again? Would you say that there would this be the type of non-locality that you've been looking at, or is this a third type of non-locality, or do you have some explanation of what's going on here within your framework?
Yes, this is a very nice question. I think I think it's a different kind of non-locality with respect to the one that I was describing, and but it's also explainable in a similar way, in the sense that so how can I explain this? So in the case of the interaction-free measurement, there is a particle which is truly superposed across, say, 2 branches of the interferometer. So then you can measure where the particle, so then you can do something on one arm and not on the other, let's say. And this will have an apparent effect. So if you do something on the left arm, this appears to have an effect on the right, on the branch of the right path, even though effectively there's nothing on the right path happening, or there doesn't seem to be anything. But the point is that you're doing something on one of the branches of the superposition. So if, as it were, your particle is now, you know, in the first quantized picture, you would say is an extended object which is present in both branches. If you are an Everettian, or if you're not an Everettian, you can think there is a probability for the particle to be on one of the 2 branches, and so on. So somehow, I think in all interpretations of quantum mechanics, you would think of this as an extended object which has some component, non-zero component, on the branch where you're doing something.
But it's non-zero, but it could be vanishingly small, right?
Yes, but true, but it is there. So there is something. So there is like a very small component of that thing on the side of, you know, where you are placing your device, which not device, I mean whatever thing that you put in there to do this interaction-free measurement type thing. In the case of the AB, on the other hand, what happens is a bit different. So in the sense that if you treat, so there are some subtleties to do with quantum field theory. And I kind of like your question because it's challenging a bit this fact. But let's say if you go by the idea that you can confine the electron very much on its path, and you kind of consider it as being superposed across these 2 different locations. On both locations, there is literally nothing occurring. So the solenoid is at the center, and it's not really doing anything on either of the branches, apparently. And yet you get the phase. And it cannot, so that I think there were calculations where people were thinking, oh, it could be some fringes effect due to the fact that there is a leakage of the wave function. You know, there's a non-zero component of the wave function over the solenoid point, or maybe the solenoid is not perfect, and that's why we see something. But actually, that's not the case. So you can't explain the phase in that way. So it's an additionally puzzling type of non-locality, because it really seems like it's magic, right? So there's this thing in the middle that does something. And then when you switch on and off the current, when you ramp up the current, at some point you will see a different phase on the electron, even though at that point the field, the transient has gone and the field is now zero at the electron, on both branches of the electron wave function. And in the case of the interaction-free measurement, if you write down the Hamiltonian, or what, if you try to describe what's going on in that interferometer, you will see that there is a direct interaction term between the whatever qubit or particle which is superposed and this gate or element that you place on that effectively only affects one of the arms. But effectively that is like a control gate on that particle, because it says, if the particle is on this arm, then do something. If the particle is on the other arm, don't do anything. And if you write down the Hamiltonian, it's going to be like a two-body term interaction between this gate and whatever qubit you're using. So there is a direct interaction that kind of explains what's going on. And if you look at it in terms of Q numbers, it's a local one. Whereas with the AB effect, this is not so straightforward to see, because you've got the charge and then the solenoid is somewhere else, and really you should write this interaction with the photons, but this wasn't done initially, so that was the thing that puzzled people.
Yeah.
They were trying to treat this the same way as you do, just with the standard charged particle in an electromagnetic field, the same thing that you use in order to compute, say, Zeeman effect and other things in atomic physics. And somehow this, substituting P with P minus A and so on, leads to this weird situation where the B, all the fields are zero, and yet A has an effect on the charge, which is kind of superficially it seems a bit puzzling. And then you have to dig very deep in order to understand why it's actually not a problem.
Yeah. Yeah, that's a nice way of saying why it's different to my example. Okay, thanks. I see we have another question from Enrique Gomez. Let me promote you to a panelist. You should be joining us now.
Hi, Chiara. Thank you for that wonderful talk. I just have a very brief question about one of your latest conclusion items, where you talk about searching for a local expression of physics, always as a guiding principle. In many books in quantum field theory, for instance, if you look at Strachey's non-perturbative quantum field theory, etc., they think of nonlocality as the signature of gauge theory. So, for example, he takes Gauss's law as the defining feature of gauge theory, and Gauss's law, because essentially you can tell me how much charge there is in the bulk of a region just by looking at the flux, electric flux at an enclosing boundary of that region, is a non-local correlation, right? In the sense that at any instant I can do that. And would you disagree with Strachey on this? That so for Strachey, non-locality is irrefutable. It's a part of physics, because it is embodied in Gauss's law. So yeah.
Yes. So I think I would disagree with that, or maybe I would agree depending on what you mean by locality. So Gauss's law is well. Let me kind of step back for a second. Here we're really talking about theories of physics, and in a way you can have a model for a situation which is a non-local model. But that doesn't mean that what's going on there is non-local. It just means that your model is non-local, and then there could be a different model which is local. So the point is that so long as you can find a local model of what's going on, where the principle that I wrote earlier, the fact that transformations on, say, a region, well, once you have the distinction in subsystems, a transformation on one of the subsystems cannot affect the others, then you can claim that the situation, whatever going on there is actually satisfies the principle of locality. You could, though, try to provide a different model of what's going on, maybe neglecting something or treating something in a different way than compared to what it should, and then you will get a non-local description. But fundamentally, if you find one that is local, then I tend to think that actually that means that the thing is local. So in the case of what you said, you can have a semi-classical model that describes some, for example, the case of Gauss's law. So in that case, you would be treating the electromagnetic field as a classical background. The charge is just a charge, and then you kind of, you do your mathematical manipulations and you will find out what you just said. But what I'm saying is that if you now try to understand microscopically what's going on, and you consider a dynamical transformation, let's say, on the charge, and you want to see what's the effect of that dynamic transformation elsewhere.
Sure.
The only way to kind of assess that, which is complete and satisfactory, is really to quantize the field and see what the effects are on other charges. So first of all, locality is about what happens should you change something. So it's a kind of dynamical property. In that sense, maybe we're not using the same language.
Yes,
right?
That's right.
So in that sense, maybe I don't disagree. I just kind of agree. It could be a mathematical feature of your model. But if you talk about locality in the way that, say, no signaling and I think also then you see that what I just said is still satisfied even in that case.
Okay, sure. Okay, then I agree with you. Yes. Okay.
Cool.
Okay, we're nearing the end of the hour, but let's see if we have one more question, perhaps. Let's see. No, I think looks like people are all happy and on board with your talk now, Chiara.
Great.
So yeah, thank you very much for coming and giving this talk. Super interesting stuff. Hopefully,
thanks so much.
Yeah, we're not so far from each other, Oxford and Cambridge. So hopefully, when the pandemic is over, we will bump into each other at some conference or something. But
yeah, that would be great. Yeah, thank you so much. Thanks for the questions. And yeah, just if you have follow-up questions, just email me. And otherwise, I was very happy to give this talk and to kind of answer these nice questions.
Cool. Okay. Well, so thanks everyone for joining in. I'll see you all next week. And for the members of the group, we'll have the normal group meeting following now. So for all the master students, PhD students, and postdocs, please stay on the link and we'll proceed. And then for everyone else, see you next week. And thanks again, Chiara.